So we are going to look at a very specific discrete probability distribution. This is known as the binomial distribution. I'm going to look at this very specific problem. Um, I'm going to go ahead and run my setup. This one again is using, I don't know why I've used these, but we're using the ARM and the weighted.discrete.stat packages. We are going to need these things here. I'm going to show you why in a little bit, but I just want to point them out there. Okay. So now I have those two things there. The probability distribution, the binomial distribution, I should say, is where you have basically certain properties that go with it. Many of the discrete probability distributions that we work with, you can't actually calculate what it is because you can't write out your sample space. In this, you actually have to conduct the experiment to figure it out. In this case, with the binomial distribution, you actually can calculate it without actually doing the experiment. The problem with this is you have to actually know that you have a binomial experiment. And again, it has certain properties. The first one is you have a fixed number of trials. You know exactly how many times you're going to repeat the experiment. It's not like you're going to repeat it till you get to a success. You're just going to keep repeating it forever. Um, you're going to have the and trials are independent. So every time you do repeat it, you're going to have those trials be independent. In other words, one does not affect the next one. The next one is that there are only two outcomes. Bi means two. There are only two outcomes. We call them success and failure. Success doesn't mean necessarily a good thing. Failure doesn't necessarily mean a bad thing. It just means that success is what you wanted to have happen. Failure means it's not what you wanted to have happen. So you could have it heads versus tails, pass versus doesn't pass, hit versus miss. You found a defective item, not a defective item. Things collapse, they don't collapse, those kind of things. So the probability of success doesn't change from trial to trial. That's also kind of an important one. All right, so some examples of this is you toss a fair coin, you have 20 people in a class, and you want to know what's more than half will pass. You are shooting at a target, and you want to know how many times how many probability of hitting it. So these are some examples. The formula is not a fun formula to work with, so we are going to use R. This is the number of combinations. This is the probability of success raised to a power. Probability of a failure, which is Q, which is 1 minus P to the n minus R power. So it's not a fun thing to work with, and it's really not fun if you're doing probabilities of X being greater than or equal to or less than or equal to. So we are going to use RStudio. The probability of X equaling a certain value. In other words, the number of successes equaling a very specific value. You're going to use D binom, D binom for binomial, D because you're going to try to find a value. Then you type in what value you want to find for. N is how many times you repeat the experiment, and P is your probability of success. If you're doing the probability that X is less than or equal to R, then you use a P binom instead. Very much the same, except you're doing lower tail is true. And that's because you're shading, you're going below. So you're always thinking of being on the bottom. Probably the X is bigger than or equal to R. That's the other way. There's a little difference here. It's one R minus one because if I say I'm going to say three or more, well, the complement of being three or more is being less than three, which is two or less, because you can't be 2.5. So we have to subtract that one off to say where we're actually starting. So that's why it's written this way, and then the lower tail is false because I'm not looking to the left, I'm looking to the right. Okay. All right, so here's my problem. According to the Auburn University website on honeybees, beekeepers across the United States lost 45.5% of their marginal honeybee colony from April 2020 to April 2021, according to the preliminary results of the 15th nationwide survey conducted by the nonprofit Bee Informed Partnership, or BIP. Commercial honeybee operations are essential to agricultural production in the United States, pollinating $15 billion worth of food crop each year. Honeybee colonies are moving around the country to pollinate important architectural crops such as almonds, blueberries, apples, and so forth. So the loss of this is going to be a major loss to our food production and supply. So a commercial beekeeper manages about 500 colonies or more. Let's look at a commercial beekeeper that actually manages 500 colonies. We want to see how many bee colonies are lost. So let's state our random variable. We're going to argue that this is in fact an binomial experiment, but let's first state the random variable. So here we're actually going to be counting. So our random variable is counting the number of bee colonies that are lost. And the reason we're doing that is because everything we're told in here is about loss. The probability is about loss. We're talking about loss and what happens if we have loss. We're looking at the probability of bee colonies being lost. So everything's about being lost. So again, it's not a positive thing, but it's still considered a success. We're then going to argue that this is in fact a binomial experiment. These are questions you should ask. So we're going to not just say yes and no. We want to actually think about why. Are there a fixed number of trials? Well, this one is a yes, but that's because there are 500 colonies. We're not going to just say a number. We're going to actually say exactly how many. And then we want to know if they're independent. Well, this is a little questionable because if they're one beekeeper's colonies, then one colony may actually affect how another colony is. If the beekeeper is not a good beekeeper, that might affect whether or not the colony survive. If one bee colony gets a disease, it could give it to the other bee colony. So there's some questions about whether or not this is independent. We're going to go ahead and say yes, because we can't do the work without that. But we're going to realize that that might actually affect what happens in the end. We're going to say yes, since one colony may not affect another. But again, this may not be true. Are there two outcomes? Yes. Either it survives or doesn't. Either it collapses, it's lost, or it is not. And is the probability of success the same for every trial? Well, yes, we were told that there's a 45.5% chance that they're lost. Okay. So now I'd like us to just state our N and P value. We actually already did. We had them up there. We just didn't call them N and P. So N is how many colonies. There were 500. P is the probability of success being lost. That was 0.455. Now I'd like to find the probability that none of the 500 colonies are lost. We're going to translate this question into a probability. It's better to kind of think of this as, can we write this in a mathematical statement? So the probability that none are lost means that the number lost is equal to 0. There's none lost. Because there's none lost, we have that. So I'm looking at this, I'm looking at the probability of something equaling 0. So going back up here, that means I'm going to be using the probability that x is equal to a number, and that's this D binom R, N, and P. So coming back to my problem of where I am, we're going to insert an R chunk. We're going to do D binom. And we have, and notice it kind of tells you what to put in. So it says my X, that's the number that's inside the parentheses. My size, that's my N, and my probability was 0.455. You don't need to worry about the log equals false. I'm not going to worry about that part. I do this calculation, and this gives me a really weird looking number. And it actually is 1.57 times 10 to the negative 132. So that's what that E represents. Computers can't write times 10 to a power. They can't write scientific notation. So a lot of computers and calculators will write it in this form. And so that number after that E is, in fact, your exponent on your 10. The main thing is that's an incredibly small number. So I don't really care exactly how many this is. This means 131 zeros and the number 1. So it's an incredibly small number. Okay. Now let's find the probability that 300 colonies are lost. So this one again, I'm going to write this in a mathematical statement. Lost is equal to 300. And then I can insert my R chunk. I'm still doing equals, so it's still a D binomial. And again, my size is 300 because that's what's in my parentheses, my 500, and my 0.455. So it's really unlikely that none were going to get lost. 300 is a little bit more than half, and it's still unlikely that you're going to lose 300, but it isn't as unlikely because this number is not nearly as small. Now, let's see what's the probability that at most 300. So at most being lost, at most is that much or less. So we're either less than or equal to 300. Because at most means we're going to come up to that value, but nothing more, but we can be anything less than that value. So looking at that, if I look at my R chunk here and come back up here to my R values, and I see that if I'm less than, here's the one that's less than, then I have this P binomial and all that information, lower tail true and everything. So coming back down to my problem, coming back down to my problem, here's my problem. We're going to do P binomial, not D, but P binomial. We're going to do our number that's in there, that 300. We're still going to have our N of 500. We're still going to have my 0.455. But now we need that lower dot tail is equal to true. And the true is all capitalized. So that's what I now want to do because I'm saying I'm less than or equal to. I'm looking at being below my lower tail. Think of it as on the lower end. That's true. Run that, and there's a 100% chance that that's going to happen. It really isn't 100% chance, but it's rounding wise, it's what happened. All right, so let's try another problem. So let's find the probability that most 100 colonies are lost. So the probability of lost being at most is again, that's as much as we're going to get up to. We're not going to get any higher than that. And so that again is that P binomial. Oops. P binomial. And then we have 100, the 500, 0.455, and the lower dot tail equals true. By the way, you can just try just a T, a capital T, not the whole word if you want to. I don't like doing that because sometimes I have a hard time seeing just a T over an F, but you can do it. So there's a chance, pretty small chance, but there's a chance that at most 100 will be lost. Now I'd like to find the probability that at least 400 are lost. So now we're looking at least, again, we're still using that P binomial. But instead of being just, and I didn't write it in a mathematical statement, so let's do that first. Our mathematical statement would be the probability of the lost is at least, so greater than or equal to my 400. So this is a greater than or equal to. Coming back up here to how we calculate these, greater than or equal to means we're doing that P binomial, but now we're going to subtract 1 from that R. Again, it's because we're saying we're at least 400, and so we want to add up everything from 400 up, or we want to subtract off everything from below 400, which is up to, but not including 400, which would be 399. So back down to here. what I see I have is I'm going to have 400 minus 1, then my 500 and my 0.45. And now my lower tail is false. And again, the false has to be all capitalized. And that again is a pretty small number. Now we'd like to know what is the probability that at least 200 are colonized or lost. So again, my lost is being greater than or equal to 200. Same thing, insert in our chunk. We're going to do that P by that P. And the way I kind of remember this is P is for probability, D is for dot. So it's not really exactly correct, but it just helps me kind of remember it. It's 200 minus 1, 500, 0.455, and lower dot tail equals false. Again, one thing to remember is anytime you have a false there, you want to have that minus 1. You also could just write an F instead of the whole false. Again, I don't like doing that because I have a hard time telling the difference between F and T sometimes when I'm looking at it fast. And there's a pretty good chance that that's going to happen because that number is really close to 1. So is it unusual for at least 400 colonies to be lost? Why or why not? Well, no, yes, because the probability of at least loss being greater than or equal to 400 is much less than 0.05. And we know that because we did that calculation. We did that calculation right here. We found out to be a really small number. So now the question comes in, is it unusual? If it is unusual to be lost and it actually does happen, what might you think? If it's not unusual and you get at least what happens, what might you think? So we did find something unusual. So we want to think about what does this mean to us that we got this unusualness? And what it kind of says to me is it kind of says to me that this shouldn't happen. If something's unusual, that shouldn't actually happen. You know, your chances of winning the lottery are really unusual, and I don't think you win it very often. So it shouldn't actually happen, but it does. So then the question comes in, what does it say to me if it does actually happen? So it says a couple things to me. If it actually happens, then a couple things. Whoops, spelled happens wrong. It could be that they weren't independent. The trials weren't independent. And I kind of mentioned that at the start, that this could be a problem. So that could be the problem. I shouldn't say were not, but could not be, might not be. Because I don't know for sure. That could be a possibility. Or another thing is, where'd the 45.5%? That came from data. So that 45.5% could be wrong, could have changed. So that's the other thing that could actually be the reason why. So there's a couple things, and it could have just been by chance. That it just happens. Sometimes things just happen by chance. The last thing I want to do is just show you how to calculate the mean, variance, standard deviation of a binomial experiment. Draw the graph. This is actually the same thing we did when we just did discrete probability distributions, so there's nothing really new here. You would find the probabilities, and you can find the probabilities. Let's say we have 10 items and your probability is 50% or 0.5, then you can actually calculate all of these by doing D binom 0 to 10, 10, and 0.5. You do the calculation, it will calculate all those for you, and there's all your numbers. And then if you want to actually show all those numbers, you can also do that. So this is the probability of 0. This is the probability of 1, 2, 3. So if I wanted to, I could actually have also put in 0 colon 10, and it would write those out also and put them in the same order. Oops. And you can kind of see how they fit together. So in this example, and then once you do that, then you know how to find everything. And you'll need to save them. So you could save them in column anything you want, column R, column prob. I don't care what you call them. You type them in and column what you want, and then you could find out what they are by just typing in R and prob. We're going to do the same thing for this problem. So we actually already put these in here. We did the R and prob at the beginning. I'm going to go back up there and show you what they were. I called prob where I was doing the D binomial, calculated for every single value from 0 all the way to 10 when my n is 10 and my probability is 0.5. And then, and in fact, we're going to do it for this example. So we're going to change that to 0.455, and we're going to change this to 500. So we want to do it for the problem we're dealing with. And then, so that means we also have to go this 0 to 500. And then the same thing here. We want this to be 0 to 500. I'm going to rerun this. So I've saved these now. I've calculated all the different probabilities for this. I've calculated all these probabilities, these R values from 1 to 10 to 501. Okay. And now I can come and do all my calculations. So I can do every calculation I've been doing in the past. Now, same idea. So I'm going to do my R chunk. I have these now saved. You could have written them here if you wanted to. I now can do that. I can do my w.mean of R and prob. I can do my w.var of R and prob. I can do my w.sd of R and prob. I have mistakes, so let me go fix that before it yells at me. I can do my discrete dot histogram of my R and prob. And again, that bar dot width is 1 is just so I can have the bars touch. And if you want to title, it's main instead of title. And then my title could be something like colonies collapsing or lost. Let's call it that way. And if you want to, you can then do your X lab is lost, number lost, and your Y lab could be probability. And then you can run that. And you can see on average, 227 are going to be lost. With a standard deviation about 11, so not a huge standard deviation. I don't know why this didn't work. Why didn't my Y lab work? Let's just take out the Y label. Maybe it won't need it. And so again, here's my probability. So there's not a big standard deviation. There's not a big variability, but you can see kind of it drops off, and it will drop off as we get farther and farther and farther away from this. This looks like a nice smooth curve, but it really isn't, because you can see the jaggedness of it here, because it did actually calculate discretely at each of those values.